Okay, welcome everybody to physics. We're talking about Newton's laws. We did a couple demonstrations, and the first thing we talked about was inertia. And inertia is the tendency of an object to maintain its state of motion. And we said that the measure of inertia is mass. So the more mass we have, the more inertia we have. So it's always easy to put yourself in the middle of something, a situation, if you're trying to figure out energy or inertia or something like that. Would you rather get run into by a kid on a bike going 10 miles an hour or a car going 10 miles an hour? Well, the car, right? Because the car has more mass, therefore it has more inertia, and it's going to affect you more, right? It's going to take a bigger force to change that velocity. Let me rephrase that. Only if you're suicidal do you want to get hit by the car, which most of us, thank goodness, are not suicidal. You don't want to get hit by either, but if you had to make a choice, you'd rather get hit by the bike because it has less mass and less inertia. So Newton's first law then is called the law of inertia, and plainly stated, it's things tend to maintain their state of motion. So if something's at rest, it'll stay at rest. Something's in motion, it'll stay in motion, unless acted on by an outside net force. So this is the way that we symbolize net force. Officially, it's this symbol. It's the summation of forces causes a mass to accelerate, which ends up becoming Newton's second law. Okay, so Newton's second law is the summation of forces causes a mass to accelerate. If we look at that, we have a box. Here we have a couple people pushing the box. And let's say this guy is pushing with 10 newtons in that direction. And we have this guy pushing in that direction with 5 newtons. What's the summation of forces in this case? Well, the summation of forces is 10 plus 5 equals 5. So the box, if let's say the mass is 10 kilograms, so kilogram is the base unit for mass for us, even though, or grams is actually the base unit. We use kilograms of because we're massing big stuff like planets and people and things like that. So in this case, summation of forces causes the mass to accelerate, or the acceleration of the object is the summation of forces divided by the mass. In this case, the summation of forces is 5 newtons to the right, divided by 10. The acceleration then is 0.5 meters per second squared. So that's pretty simple stuff. I'm sure you all did that in physical science. So the question was, is it true if you don't have acceleration, you don't have a force? Well, it could be true, but it's not necessarily true. Because if we have the same box here, and we have a push on this side of 5 newtons, and we have a push on this side of 5 newtons, the summation of forces in this case equals 0. But there is still force occurring here. So really, maybe you're thinking summation of forces. And that is the case. If there's no acceleration, then there is a summation of forces always equal to 0. So the question is then, when you go down the road in your car, you're cruising along at a constant speed, constant velocity even, at 20 meters per second, do you have to put your foot on the accelerator? The answer is yes, right? Why do you have to put your foot on the accelerator? Because when you put your foot on the accelerator, you would think that you would accelerate. But what's happening here? Friction, very good. So there's friction. So if our velocity is in this way, then let's think of some of the forces that are on the car. Well, okay, so the road, now something funny about rolling friction. So if a tire is rolling this way, then what's actually happening is you keep reinventing the surface as you roll. So there's actually very little friction slowing it down due to the rolling. Now, if it's a real bumpy road, that'll be different because it'll actually force on the tire. But if it's a smooth road, there's not a lot of friction. The friction that does occur though would be called intermolecular friction. So what that means is, you know, you have a whole bunch of pluses and minuses that this car or this tire is made up of. And then also on the road, you have a bunch of pluses and minuses that the road is made up of. And so there's a force of electricity and this intermolecular attraction to the other molecules then is one part of friction. The other part of friction is, you know, everything, even solids, actually have, you know, flexibility to them. So in reality, if you roll across the road, if you could see on the molecular level, you know, needless to say, you don't ever actually touch anybody because the force of electricity, we'll talk about that later, is so great that it's stronger than gravity. So this car is essentially floating across the other molecules. Maybe that's not needless to say. But regardless, what happens is this force actually dents in the surface a little bit. So if you could see on a molecular level as the car is moving along, it'd be almost like going through water where you'd have a little bit of a bunch up there and a divot, almost kind of like a wake in the boat or something like that. So that is also another cause of friction. But besides those two causes, which are pretty small on rolling friction, there isn't much. So where does the friction come from that we were talking about? It comes in here, where there's an axle, and the wheel is actually moving along, you know, the axle, or the axle is moving with the wheel, depending on what kind of vehicle you're driving. And that's where you get a lot of friction. So that would be the force of maybe the axle and wheel. Is there another force of friction slowing this car down, or wanting to slow this car down? The force of air is another one. And so we have the force of the engine then is going to be causing the car to move in that direction. Now the force of the engine is something we need to talk about a little bit more in greater detail when we're talking about Newton's third law, which is not going to be today. But the force of the engine is going to cause the car to want to accelerate this way. And I won't go any further in that case. But then we have the force of the air, we have the force of the friction of the wheels and things. And that's why we have to push the accelerator. So we end up getting a summation of forces equal to 0, which then we can maintain our state of motion. Okay. So then Newton's third law, this is the hardest law for people to understand, is for every force, there's an opposite in direction but equal in magnitude force. So we're going to go into great detail on that later, but just for now, know that for every force, there's an opposite in direction but equal in magnitude force. Okay? Keep in mind, you can't push nothing. We're going to elaborate on that quite a bit, though. There's a lot to that one. So for now, what you have to know for the worksheets and stuff like that is the force of gravity is m little g. Okay? Or the weight of a person is mass times little g. Okay? And so the weight of a person here on Earth is the measure of the attraction that you have to the Earth. If you go to the moon, your weight on the moon would be much less because there's a much less force of gravity on the moon, but it would still be your mass times little g on the moon, and that's called weight. Okay, and we'll talk about a little bit later. Force of gravity is actually big G m over r squared, and these are the two masses that are interacting, which in your case, if we're talking about this right here, it's the mass of the Earth and the mass of yourself. This is the r is how far you are from the center of mass, as long as it's a regular mass. We'll talk about this in more detail later. But for now, know that weight of any object is equal to the mass times little g on or near the surface of the Earth. Okay, so we need to look at what we call free body diagrams. Okay, so this is a big one. These are always part of the AP test. free body diagram. Okay, so kind of the rule for this is you draw all the forces acting on an object. So you draw all forces acting on an object, but you draw no reaction forces. So when we talk about action-reaction forces, we're talking Newton's third law. So just put in no reaction forces. Here's what you have to understand too is when we draw these forces, we're going to use vectors, or a force is a vector. Okay, so it has size and direction. And so when we used vectors before, we had an arrow, right? And this was the number or the magnitude. So the size mattered because that was how big the vector is. And then the direction is indicated by the arrow. Okay, so it's really important to be able to draw these because they determine how your math goes. So we're going to give some examples. Let's say that we have a table here, and we have a box on a table. Okay, so I want you to come up with some force vectors for this object. Okay, so this is always a force vector. If anything has volume, it takes up space. If it takes up space, it has mass. If it has mass, it has weight. So absolutely, without a doubt, every free body diagram will include the force of gravity. And so you can label this weight, or I usually do F subscript what I'm talking about. So F subscript little g, F subscript big G, weight, F subscript mg, any of those. Okay, all right. Okay, so now are there any other forces acting on this object? Keep in mind this thing is at rest on the table. We got a kid from physics last year said the force of the normal. Okay, so what in the world is the force of the normal? Well, the force of the normal is, there's kind of two definitions to normal. The force of the, first of all, normal is perpendicular to the surface. That's like an old framing term from thousands of years ago. So if you had a normal, something that was normal, it means it's perpendicular to the surface. And so that's the first indication. So here's the surface. This is the surface here. The normal has to be perpendicular to that surface. Okay, and then the other definition of it is the amount of force that the surface applies to the object in order for the object not to fall through the surface. So in this case, the force of gravity is defined by this length. The force normal then has to be the same length as that because they're the same magnitude, but they're opposite directions. Now, they are not action-reaction pairs. What is the reaction pair to the force of gravity? Anyone know? This is the Earth pulling on the box. What's the reaction pair? Right, the box pulling on the Earth. So the force of normal in this case is equal to, in magnitude, the force of gravity, but it's not the action-reaction pair to the force of gravity. Okay, any questions on that? Okay, so now let's have another one. So we now have another table and box situation. Here we have our box, and we'll say that this has a constant velocity, constant v, okay? And we'll say that there's a finger here pushing on this, and it's got a constant v. Okay, but what do we always have? Gravity. So we got gravity, force of gravity. What do we have to have so it doesn't fall through the surface? Force normal. Okay. Now, is there a force of the finger? Yeah, you can see it's forcing in this direction. That's the force of the finger. Now, is there any other force? It has to be something going opposite of the force of the finger, right? Because if not, it would be accelerating in the direction of the finger. So there must be the frictional force here, or the force sub F. I always do friction with a little f myself, because if you look at the formula for friction, it kind of has that little f. Okay, any questions about that? Okay, God bless you. Let's look at another one then. Okay, so this is our ramp, and in this case we have a box here, and we'll say that this is stationary. Okay, so we have a stationary box. First one we always have is the force of gravity, right? Okay, now, do we have a force normal here? Okay, what was the first definition of the force of normal? Perpendicular to the surface, and the second definition? Yeah, so it's first of all, it's perpendicular to the surface. Second of all, it's the amount of force that it needs to keep the box from moving through the surface. So we have to look at our vectors here. So this is the force of gravity. This would be the force, the part of gravity that's down the ramp, which would cause acceleration, right? This here is the part of gravity that's aimed into and perpendicular to the surface. So whatever this part of that triangle of gravity is, that is the number for the force normal. But the force normal is opposite direction. Does that make sense? So in this case then, our force normal is this with, this being equal to this in magnitude. Okay? Okay, the drawing is not perfect. But anyway, this then would be called the force normal. Okay, now, this thing is stationary. And if there's a force that's down the ramp, we better label that, right? This is something that's kind of up for, I don't know. This isn't actually a real force. This force down the ramp is not a real force. It's the mathematical description of how much of gravity is in the direction of the ramp. It's not a real force, though. On the AP test, should you label it as a real force or not? I wouldn't. But I had, quite a lengthy discussion about it one time when I went to an AP convention. I wouldn't label it myself. But why is that important? Well, if we're trying to figure out acceleration down the ramp, or if we're trying to do a summation of forces, we would use this number. Is it a real force? No, it's not. The real force is gravity. But if this is stationary, there must be a force that's equal but opposite to this, which would be what, Sage? The friction. So this here is a real force, and that's the force of friction, and that's going to be equal in magnitude to, except opposite direction, to the force of gravity that's down the ramp, or the part of gravity that's down the ramp. So there's your free body diagram for this one. We got gravity, friction, we got normal. Okay, any questions on that? Good question. Okay, so here now we have same picture. Okay, but this time it's a constant velocity. Okay, so I want you guys to figure out what the free body diagram should be on this. Down the ramp, constant velocity, down ramp. Okay? Okay, so we know we always have that force of gravity, right? And it says constant velocity down the ramp, so there has to be friction that's equal in magnitude, opposite in direction of that part of gravity that's down the ramp when we draw a right triangle. Okay, so that's the force of friction. And then our normal comes straight out of the ramp. That's equal in magnitude as this part. So it's the same free body diagram as we had before, right? So stationary, constant velocity, both summations of forces are 0. No acceleration. So you can have summation of force equal to 0, but still have motion. Okay? So let's look at another one. Let's say that we have the ramp again, but this time we have acceleration down ramp plus friction. Okay? Pause the video and give that one a try. Okay, so if we look at this, well, we have force of gravity, And then we have friction. Okay, so this is the part of gravity that's down the ramp. So our friction's got to be less than that, of some kind, right? It's got to be less. Okay, and then we'll have our force to normal that is still equal to this in magnitude but opposite direction. So that would be our free body diagram for acceleration down the ramp. Okay. Okay, you know, one thing that you need to know always though is friction. Friction can never cause motion. Okay, so keep that in mind. We're going to have a lot of problems where it might look like friction might cause motion. Friction can cause acceleration if it's slowing an object down, but it will never be greater than a force that opposes it. So the actual formula for friction, and we'll talk about this later, is less than or equal to the coefficient times the normal. We'll talk about that in great detail. Thanks for bringing that up, though, Tyler. So back to another free body diagram. So you got a little string here and a ball and a string. So see if you can draw that one in. Okay, so what do we always have? Well, we always have force of gravity. Okay, if this thing is stationary, there has to be something opposing gravity then, right? Well, in this case, if it's a string or a rod or something like that, we call it tension. So this would be the force of tension, and this should be the same magnitude as that. Okay, any questions? So let's have another one, since there are no questions. Okay, let's have a string here, a string here. We'll call these two theta. See if we can do a free body diagram of that. Okay, well, force of gravity, right? Now we have two tensions this time. Okay, so let's say that force of gravity is X. Okay, and so we have one tension in this direction and one tension in this direction. Since these thetas are the same, then what happens is this piece and this piece over here, those are both not X but half X. Okay, so together the Y parts of these tensions, which I knew this solid line should have done that. The Y parts of these tensions are going to have to equal the Y part of this force of gravity because there's no motion there, right? Well, there's no motion left to right either, so then we have to realize that the X part is canceled out by the X part of the other tension. So the pull from the tension here is canceled out by the pull from the tension here, and then the tension up here plus the tension up here equals the force of gravity. Any question on that? So we got a lot of arrows and stuff here. So the actual free body diagram then for this would be force of gravity and force of tension 1 or 2, and then force of tension 2. And those three there are the actual free body. That's a free body diagram. But the length of these is determined by this stuff. Firstly, it's determined by the force of gravity, and then this has to be canceled out by this. So, does that answer your question? Okay, and then we have one more I'll show, and then I'll let you do some practice. So we got this situation like this. Okay, see if you can do that. Okay, so absolutely we have the force of gravity. Okay, and then kind of the thing that messes with you a little bit is the shorter rope, or the shorter rope in these are always the bigger force. And we'll talk about that and how the math works out later. But like if you're on top of something lifting it, it's going to be a lot harder than if you're off to the side just kind of pulling it, right? So in this case then, this force of tension here is going to be big. And if you look at how big your other force of tension is, it's really going to be determined by this x here. Okay, so however big that x is how big the next x has to be. So then your other force of tension then would be right there. This is the free body diagram, okay? Keeping in mind that this x is equal to this x for magnitude, so there's no movement lateral. But then also this y, so that y1 plus this y2 has to then equal the whole entire force of gravity. Okay, so this force of gravity then equals y1 plus y2. And it is opposite in direction, but this is vector addition. So really, if you want to see that direction, then you would say force of gravity minus y1 minus y2, which gives our direction that is equal to 0, equals the summation of forces that equals 0 acceleration, which isn't really the equation, but. Okay, so those are your examples. Let's see what you can do with that first assignment.